In this video, we will take a look at our remaining intermolecular forces, including dipole-dipole forces, hydrogen bonding, and ion dipole forces. So in our previous video, we talked about the dispersion forces. We said those were found in all substances, and they were going to be the result of the random movement of electrons leading to temporary dipoles, which could induce dipoles and attract one another. Our next force, the dipole-dipole force. This force is going to be the attraction between partial charges on neighboring permanent dipoles. So this is our difference here. Dipole-dipole are temporary, or dispersion are temporary. Dipole-dipole are permanent dipoles. So if we think about what contains permanent dipoles, those are going to be polar molecules. So our dipole-dipole forces are found only in polar molecules. Now these are still fairly weak intermolecular forces. They're stronger than our dispersion forces, but they're still fairly weak. Their strength, however, depends on the magnitude of the dipole. The more polar the molecule, the stronger the dipole-dipole force. So our dipole-dipole force, if we have a polar molecule, so say we've got this molecule, we've got a formaldehyde, where my carbon is partially positive, my oxygen is partially negative, and I have a dipole. So I've got one end of this molecule up near my oxygen, or one corner of that triangle with the oxygen is going to be negative. The other side of my triangle is going to be positive. So if I have another formaldehyde nearby, which also has those partial charges, we're going to have the attraction between the negative oxygen and the positive carbon. That's going to be my dipole-dipole attraction. So with our dipole-dipole forces, similar to our dispersion forces, we need to be able to compare them across molecules. So here we're given a series of molecules, and we're asked which has the strongest dipole-dipole force. So again, if we're judging dipole-dipole force, we are looking at polarity. So whichever is the stronger polar molecule will have the stronger dipole-dipole force. So we did this in a previous worksheet with our polarity review. We looked at ranking polarities. Our trend for stronger dipole-dipole force is going to follow that same ranking. So we need to look at these and identify who is more polar. Now remember we said that we could technically look at these formulas without drawing them out. Remember our carbon's our center atom. If we look at all of these, I've got hydrogens with bromines. That means all of these are going to be unsymmetrical. And if my molecule is unsymmetrical, it's going to be polar. So these are all polar molecules. So we're going to compare their polarity. Now, they all have bromine. So when we're comparing the polarity, we've got to look at how many polar bonds. And remember, the greater number of polar bonds we have, the less polar my molecule is. So we could count our number of bromines. The more bromines we have, the less polar my molecule is. So if we were to judge based on that, we would have the CH3, or sorry, the CHBr3 being the least polar, then the CH2Br2, and then the CH3Br. But we could also draw these out. So I could have my carbon in the center with one hydrogen and three bromines. My CH2Br2. And then my CH3 Br. So again, these all have these polar bonds to the bromine, with the bromine being more electronegative. So my dipoles all point out towards the bromines. Where I've got that single bromine, I've got a single dipole. My electrons are pulled towards a single corner of my tetrahedron. As I have a larger number of polar bonds, it becomes spread out. As the electrons spread out, the overall polarity decreases. So my CHBr3 is my least polar. My CH3Br is my most polar. The more polar the molecule, the stronger the dipole-dipole force. Now, if we had different atoms, then we could also look at electronegativity. So if we were to compare a CH3Br to a CH3F, the carbon-fluorine bond is more electronegative. And so this would be more polar than a CH3Br. And therefore, it would have stronger dipole-dipole forces. So we've talked about two forces so far. Dispersion, we find in everything. Dipole-dipole, we find in polar molecules. Next, we have hydrogen bonding. Hydrogen bonding is a type of dipole-dipole force. It's stronger than our basic dipole-dipole, and it's the interaction of a hydrogen bound to nitrogen, oxygen, or fluorine. Hydrogen bonding, very importantly, has two criteria. So this is the first one. Hydrogen's bound to nitrogen, oxygen, or fluorine. And that nitrogen, oxygen, or fluorine is going to interact with lone pairs of electrons on a neighboring nitrogen, oxygen, or fluorine. Hydrogen bonding becomes stronger with the larger number of hydrogen bonds a molecule can form, as well as the more polar the bond to hydrogen is. So again, we've got two requirements for hydrogen bonding. We have to have hydrogen present. Now, just because hydrogen is present does not mean there's hydrogen bonding. We must have hydrogen bonded to nitrogen, oxygen, or fluorine. That's the first criteria. So, hydrogen bonded to carbon cannot hydrogen bond. It has to be nitrogen, oxygen, or fluorine. The second criteria is that we have a lone pair of electrons. And that lone pair is going to typically be found on nitrogen, oxygen, or fluorine. But that's the two criteria: nitrogen, oxygen, or fluorine, and a lone pair of electrons. So next we're asked to take a look, and we've skipped a little bit ahead in your worksheet. So we've skipped over problem 6, 7, and 8 for right now. We're focusing on the hydrogen bonding. We'll get back to those other questions in a second. But next we're asked, how many hydrogen bonds can a single water molecule form? So if we look at a water molecule, I can draw my dot structure. I've got oxygen in the center, single bonds to two hydrogens, and then lone pairs. Now, the oxygen-hydrogen bond is polar, so the hydrogens are partially positive. My oxygen's partially negative. If I have some neighboring water molecules, the hydrogen bond initiates by the attraction of very negative oxygens to very positive hydrogens. So what we're going to have is these lone pairs on oxygen being very attracted to my partially positive hydrogen. That attraction is my hydrogen bond. So it's not the chemical bond to hydrogen, it's not the OH in the water, it's the lone pair from oxygen attracting to a hydrogen in another water molecule. Now, that water molecule has two lone pairs. So the lone pair on the other side can also attract to a partially positive hydrogen. So the two lone pairs on the water molecules can form two hydrogen bonds, but at the same time, that same water molecule also has hydrogens, and those hydrogens can attract to lone pairs. So on a single water molecule, each hydrogen can attract a lone pair. Each lone pair can attract a hydrogen, which means we're going to get a total of 4 hydrogen bonds per water molecule. So again, the more hydrogen bonds a molecule can form, the stronger the attractions will be. So water that can form 4 hydrogen bonds versus some other molecule that can only form 1 hydrogen bond, it's going to be stronger. We could also compare say something like ammonia, NH3, versus the water. These both form the same number of hydrogen bonds. They both are going to form 4. So what we're looking at is the difference in electronegativity of that center atom. The oxygen is more electronegative, resulting in the more polar bond, and therefore it's going to have the stronger hydrogen bonding. So we've looked at 3 forces now. Dispersion, found in everything. It's the weakest. It's due to electrons moving. Dipole-dipole is a result of permanent charge distribution, permanent dipoles. They're found in polar molecules. Hydrogen bonding is a special case in dipole-dipole or in polar molecules in which we specifically have hydrogen-nitrogen, hydrogen-oxygen, hydrogen-fluorine that can attract lone pairs, which can be a particularly strong attraction or stronger than regular dipole-dipole. Now, our final intermolecular force is the ion dipole force. It's the interaction of positive or negative ion with the partial charges on a polar molecule. This type of interaction is important in the solvation of ionic compounds or solution formation. So if we take an ionic compound such as sodium chloride and we put that sodium chloride into water, water is going to surround it. We're going to have the partial positives and negatives, so the partial negative on water on the oxygen is going to attract the sodium. We're going to attract to that positive charge. Then the partial positives on my hydrogens are going to attract to my negative charge. So my water molecule being polar has those partial charges. It's going to surround my ionic compound. The negatives on the oxygen attract the positive in the ionic compound. The positives on the hydrogens attract the negative on the ionic compound. That attraction is strong enough that it actually pulls the ions apart. Ionic bonds are very strong. That's why they're going to form these solid networks. Ion dipole force is a strong intermolecular force. It's the strongest of the 4. It is strong enough to break ionic bonds. So we have our chart here, and we're going to talk about ion dipole and our other forces when we talk about properties a little bit more in the chapter. But we've got this chart here that compares our 4 forces and what they're present in. So again, dispersion is found in all molecules, all atoms. Dipole-dipole, only in polar molecules. Hydrogen bonding, only in molecules containing hydrogen bonded to fluorine, oxygen, or nitrogen. Ion dipole, it occurs in a mixture. So these first 3, when we talk about impacting properties, they impact phase. They're going to impact boiling points, melting points, and reactions. Ion dipole because and this is for pure substances. Or mixtures. Ion dipole only occurs with mixtures, and it's specifically a mixture of an ionic compound and a polar compound. So we've got some picture representations. Remember, the dispersion is the attraction of partial charges that are temporary. Dipole, it's the attraction of partial charges that are permanent. Hydrogen bonding, it's the attraction of partial charges. Ion dipole, we have partial charges. So if we look at all of these intermolecular forces, what they all have in common is attraction of partial charges. Out of all of these forces, the only attractions to occur in nonpolar molecules are going to be dispersion forces. So we want to be able to look at different structures and identify what intermolecular forces we have, because again, those intermolecular forces are going to impact behavior and properties. Compounds will have more than one type of force. It all depends on what type of substance we're dealing with. So if we look at our first molecule here, we have CF4. It's going to have dispersion forces because dispersion is found in all materials. CF4, I would have carbon with bonds to 4 fluorines. That is a symmetrical molecule. Since it is symmetrical, it is non-polar. Since it's not polar, there's no dipole-dipole. There's no hydrogen, so there's no hydrogen bonding. And it's a pure substance. There has to be an ionic compound to be present for ion dipole, so it is not ion dipole. So it's a non-polar molecule. The only force we have present are the dispersion forces. Now next we have water. Again, dispersion is found in everything. Water is a polar molecule. We've got those lone pairs. The instant we see lone pairs, that makes it unsymmetrical. And since it's unsymmetrical, it's going to be polar. Since it's polar, it has dipole-dipole. And then we just looked at water as an example for hydrogen bonding. It has the oxygen-hydrogen bond. It has the lone pairs. So it meets the criteria for hydrogen bonding. So in a water molecule, we have 3 forces present. We've got dispersion, dipole-dipole, hydrogen bonding. Water has the ability to undergo ion dipole, but there's no ionic compound present, so there's no ion dipole going on right now. Then next we have the CHCl3. So you have a single bond to hydrogen, and then bonds to 3 chlorines. It's unsymmetrical, so that molecule is polar. So being polar, it has dispersion, it has dipole-dipole. There is hydrogen in this molecule, but hydrogen is bonded to carbon. To be hydrogen bonding, hydrogen has to be bonded to oxygen, nitrogen, or fluorine. We don't see that here, so there is no hydrogen bonding. And again, it's a pure substance. We're not seeing a mixture here, so there is no ion dipole. And then finally, we've got C2H2. All I see is carbon and hydrogen here. So without even drawing its structure, I know it's nonpolar. So whether it's carbon-carbon bonds, which are nonpolar, or carbon-hydrogen bonds, which are nonpolar, I have all nonpolar bonds. It's a nonpolar molecule. The only force present in a nonpolar molecule is dispersion. So we can eliminate the other 3. So here we have talked about our 4 intermolecular forces. We'll see them come up again. In our next video, we're going to take a look at how these forces impact properties, in particular the properties of melting points and boiling points.